Hello, everybody, and thank you for joining us today for our Insulation Intel webinar, Industrial Noise Control, Strategies for Acoustical Insulation. My name is Kim Melton, and I will be the moderator for today's presentation. So before we get started, I do want to go over a few logistics. First and foremost is we will be answering your questions today live at the end of the webinar. You can submit any questions you may have via the Q&A feature, and you should see that to the right side of your screen. If you don't see that on the right side of your screen, there's a series of circular icons across the bottom. The third from the right is a question mark in a box. If you click that, it will open the dialog box that will allow you to submit questions at any point during the presentation, and then we'll address them at the end. Next, just a reminder that this is for educational purposes only, and it should not be used as a substitute for professional engineering design, consultation, or documentation that may be required by building codes, contracts, or applicable laws in your area. If you have any questions after the webinar, you can refer to our specific application guidelines and instructions located on our website, or reach out to us directly for additional support. Also, we're going to end today's webinar with a survey, and this is your opportunity to provide us with feedback on how we've done today. You can even use it to ask any additional questions you may have about the topic of the webinar or suggest new topics for future webinars. The survey is also part of how we deliver the JM experience to you. Now, if you look in the bottom left corner of your screen there, you'll see those the people, passion, perform, and protect. Those are the 4 pillars of the JM culture. And we offer webinars like this one to help educate the market and offer a tool and be a resource for you and your business. But fulfilling those 4 pillars isn't just a one-way street. So your feedback is a key component to helping us evolve to better meet your needs. So if you have any questions or comments or suggestions on how we can better accomplish this, or even if you feel like we've maybe missed the mark today, we'd encourage you to fill out the survey, and we'll use your feedback to improve our webinars and provide information that has the most value to you. So with that, I'm going to hand it over to Jacob Lass and Scott Sinclair to introduce themselves.
Yep, thanks, Kim. Welcome, everyone. My name is Jacob Lass, and I'm the Product Development Engineer for JM's Mineral Wool line of products. I have a background in chemical engineering and experience in the process engineering industry, and I've been with JM going on 4 years now.
And good morning, good afternoon, and good evening to everyone who has joined us. We thank you for your participation. I am Scott Sinclair. I'm the National Specification Manager for Johns Manville Industrial. I actually have a background in electrical engineering with a Bachelor of Science degree. However, I've been working in the arena of industrial insulation systems for about the last 18 years, and I have been with Johns Manville for 1 year. So before we dive into the material, just take a quick look at what we would like to try and cover for you today. We're going to start with a hopefully brief overview of some basic principles of sound control, look at some different mechanisms for influencing sound control, talk about how materials are tested to look at gauging their acoustic performance and the way they can contribute to the reduction of noise issues. Then we'll look a little more specifically at some standards-related information and talk about the ISO 15665 standard, and then review results from testing that Johns Manville has done with our materials to achieve conformance to those requirements, and then end with a very brief discussion about designing an effective thermal and acoustic insulation system. So let's take a quick look at why sound control is necessary. And as I'm sure most of you probably know, one of the primary drivers for the use or implementation of sound control methods is for personnel protection. OSHA, or the Occupational Safety and Health Administration, tries to limit noise exposure to levels at 90 decibels or dBA over an 8-hour exposure period or work shift, and this is what is known as their permissible exposure limit. However, they also have another limit that's referred to as the action level, and that one is actually at 85 dBA. So they actually recommend action to address noise at a lower level than the permissible limit. Part of the challenge with looking at personnel protection is that there is a tremendous amount of variation in the requirements both looking at different organizational standards or regulatory standards, as well as different countries across the world. So it's very important to make sure you take a look at the requirements in the area for the projects that you're working on, and make sure that you are following the appropriate limits. Obviously, the big concern with trying to limit noise exposure is related to hearing loss prevention and safety. A very critical aspect of the safety side of noise control and personnel protection is making sure that employees and workers can hear safety sirens and hear coworkers trying to talk to them, especially if there is an emergency situation where being able to hear that warning or hear somebody trying to get your attention could be a life or death situation. Facilities are required to have protective measures in place to meet these requirements, and that can either be by addressing the noise source directly or by the implementation of hearing protection at the employee or personnel level. And as I mentioned, you do have to be careful and make sure you look at all the possible regulatory agencies who could have oversight on the project you're working on to make sure that you're following the most stringent requirements that particular project may have. Another aspect of noise control is looking at environmental regulations, obviously trying to control noise in the environment that may be around the facility that you're designing or working on. Again, these requirements, these limits will vary by the jurisdiction. It could be city, county, state requirements, not just federal requirements. Obviously, in many instances, communities, residential or commercial communities, get built in closer proximity to industrial facilities that may have been there originally before the neighborhoods were built, and then sleep disturbance becomes an issue. Annoyance of quality or quality of life issues can also be important. There are regulations that do restrict noise levels based on trying to protect wildlife that may be in or around the area. And then the old good neighbor regulations, you just really don't want noise disseminating from these facilities and causing a disruption to people who may live or work in and around the location of the plant. Another aspect of looking at noise control is looking at specifications related to the noise emissions of equipment. Very frequently, equipment noise levels are limited to an 85 dBA limit at a distance of 1 meter from the piece of equipment. However, the challenge with this is that only addresses that individual piece of equipment and doesn't account for the possibility of cumulative noise from other pieces of equipment that may be in the same area. And so you often will need to take into account the fact that you have multiple noise sources in a close proximity, and then look at other mechanisms for addressing the noise issue and being compliant, where the individual pieces of equipment may comply, but in total they may not. Typically, there are no noise specifications for anything that may be attached to or connected to those pieces of equipment. So any piping, stack outlets, structural steel elements that may be holding the equipment. So you may have to take those into account as well. And then you will need to also be cognizant of the fact that very often emergency equipment, so pieces of equipment like generators, often are exempted from those limits because their operation is critical for other reasons. And with that, we will take a look at moving over to Jacob and let Jacob give you a little bit of a discussion with regard to some principles of sound control.
Yeah, thanks, Scott. So now that we've kind of got a understanding of the safety aspect of sound control, we'll get a little deeper into some of the principles behind sound control. We'll start out with the fundamentals that some of you may be more aware of. We'll start with amplitude of any sound wave. As sound is emitted in a wave-like pattern, each sound wave has an amplitude which basically describes the loudness of the sound wave coming out of the source. The amplitude is essentially what controls the strength of the sound that's coming from whatever's emitting that sound in the first place. The next area that we'll get into is the frequency of that sound wave, basically more described as the cycles per second that sound wave oscillates between its high and low amplitudes. As the frequency increases, the pitch of the sound that we can perceive as people will increase. So frequency has a big part in not only what our ears can pick up, but actually how that sound wave behaves in the industry, because there's a lot of difference in the behavior between a low frequency sound wave and a high frequency sound wave. We get a little more into that detail with our third point here with A-weighting. A-weighting is an interesting concept, and we have a graph at the bottom right-hand side of your screen that kind of describes A-weighting in a graphical sense. And what it basically is it's describing the relevant sounds that your ears can pick up, that our ears can pick up as people. A-weighting is describing the basic curve between the frequency range that we've discussed before, from low frequencies to high frequencies. There are certain levels of sound and certain strengths of that sound that our ears will naturally pick up, just dependent on that frequency. But what's actually more interesting is there's another graph that you can see called C-weighting. It's that orange, more flat chart in the graph. And what that is describing is the same concept of what our ears can perceive, but at much higher amplitudes and much louder sounds, because as those sounds will increase in strength, our ears will be able to pick up those frequencies a lot more easily. I like to think of this more as the hearing test that we've all taken, where you start off with a sound that you can hear and then it slowly fades away. Even though it's that same frequency of sound, it's the strength of the sound that is truly affecting what we can and can't hear. So moving on to the typical associations with those frequencies that we've discussed before, we have the low frequencies or rumbles, which are at the very, very low end of that frequency range, the 31 to 63 hertz or oscillations per second. The rumbles are normally associated with low bass noises and vibrations, and we'll get deeper into those later. We have the roar section. It's kind of the median range of sound waves and sound frequencies, and then moving all the way up to the high frequency hisses that will more associate with piping equipment, valves, and other areas. To get more into that detail, we have that same information shown in this chart. Those low frequencies are normally associated with engines, turbines, or any vibration structures. As you move higher in those frequencies, you get more into the typical standard industrial equipment of pumps and motors, coolers, and even compressors. And then as we move to that high hissing range, that's when we really encounter piping, flow noises, valves, and anything else associated with an extremely high frequency sound wave, and any controls that we might want to put around those. The big important thing here is that not all protections are going to act the same for each frequency. Like I mentioned before, they'll have different behaviors based on their frequencies. And so it's always important to keep that in mind when you're looking at the system that you want to use, because not only what you put around your equipment is important, but also what kind of sound your equipment is emitting is also just as important. So to get more into those details, I'll pass it back to Scott, who'll talk about how to truly influence your sound control.
All right, thanks a lot, Jake. So as Jake said, let's take a look at how you can influence sound control. There's a concept for sound control that's been referred to as what's called the source path receivers. And basically this deals with different concepts for how you address noise control. The ideal solution to noise control is to address it at the source. If you can do something to stop the source from generating that noise. That's the best way to address it. If there's not an adjustment or change you can make to stop the noise at the source, then you have what's known as the path. So trying to put something between the source and the receiver to block the receiver from hearing the noise. And if there isn't a way of achieving success there, then the last resort would be addressing it at the receiver, and this would be typically in the form of hearing protection. So as I said, it's always best to try to reduce the sound at the source if you can. And as Jake was mentioning, noise sources create different frequencies, different levels of noise, and therefore there are also different mechanisms for trying to address them. When you have equipment like pumps or compressors, blowers and motors, the typical type of noise control solutions might be things like an acoustical blanket put around the piece of equipment, or if it can't be directly enclosed due to possible heat-related issues, then maybe building an enclosure around it. And then one other aspect of noise control on these would be isolation, where you're basically trying to mechanically isolate the piece of equipment from whatever is attached to it so that it can't transmit that noise into any materials that might be attached to it. Piping is very, very similar to the pumps and compressors, only instead of a blanket, you would do some type of acoustical pipe lagging or acoustical insulation installed around the pipe. You can also do silencers, which can help address the noise that's generated typically by things like flow, gas or liquid flow through the pipe, and again, isolation. Most pipe systems are supported in one way or another structurally, and isolating the pipes from that structure acoustically so they don't transmit the noise can be very important. Then moving on, looking at things like aerial coolers or fans. A very important aspect here is looking at the fan blade design, which very often will dictate the amount of noise that the fan may generate, and also looking at the drive motor and the frequency at which the fan blades are being driven, because that also can affect the amount of noise developed, and looking at possibly using a variable frequency drive so that you can real-time control the frequency at which the fan is turning. Air intakes and exhaust systems, again, putting a silencer in place, so trying to create a path that the air has to pass through that dampens out the noise at the path between the source and where it exits. And then just general background noise, again, looking at having to use barriers or buildings to possibly address those issues. But let's move on and try to focus on the pipe acoustic insulation side of this. This is predominantly where we see a lot of demand or requirement in the industrial area, looking at the system that you would apply over the pipe to try and minimize the amount of noise that is radiated from its surface. And typically that would be taking the pipe and applying some type of an absorbing or resilient material, porous layer on the outside of the pipe, and then on top of that, a lagging system that may just be a metal jacketing system by itself, or it may also be a metal jacketing system in conjunction with some type of mass-loaded vinyl, depending on the level of noise reduction you're trying to achieve and what frequency that noise is at. So very critical information there. Now let's take a look at a couple of definitions real quick as we continue looking at noise control. One of the first is a term called insertion loss, and insertion loss is looking at a reduction in the noise level radiated from the inside of a mechanism, in this case from the inside of a pipe, as compared to the noise level on the outside of the pipe. So you would basically take a measurement of the noise level outside the pipe with no acoustic treatment on it. Then you would apply your acoustic treatment measure the noise level again, and the difference between those two noise levels is basically your insertion loss, or the amount of reduction in noise level that you were able to achieve. Another commonly used characteristic of noise systems and noise reduction systems is transmission loss. And this is typically looking at the amount of reduction in noise as it passes through some type of an assembly. Very often that might be a wall or a ceiling or a floor in a building. So again, looking at the sound pressure level or the noise level at the source side of that assembly, and then looking at the noise level on the opposite side of the assembly. And the difference between those two is obviously the transmission loss that you are able to achieve. It's important to understand that insertion loss and transmission loss are different. As we just described, insertion loss is looking at the decrease in sound power as a result of adding a treatment to the outside of a piece of pipe or a piece of equipment, whereas transmission loss is a similar decrease in the sound power, but that's as a result of the sound passing through an assembly. A critical aspect to remember, though, is that while these are very, very different characteristics, the decrease in sound power could be resolved the same way through a combination of both absorption as well as reflection, depending on, again, the type of noise that you are trying to attenuate or reduce. So that brings us to trying to take a look at the different ways of addressing the noise level, being sound absorption versus sound transmission. As we said, sound absorption is a way of measuring there's a difference, between the incident sound level and the measure of the reflected sound level from that material being treated. Sound absorption is typically achieved as the result of an open cell or porous material. And in a few minutes, we'll talk a little bit more about how the thickness of that material can impact the amount of absorption that you would achieve. Whereas on the sound transmission side, that is typically a reduction of noise via sound transmission is achieved typically by high mass materials or damped materials, where you are very, very frequently reflecting the sound back to the point of origin, or possibly damping the amount of mechanical vibration in a pipe or piece of equipment to reduce the amount of noise that it generates. The key, again, here is understanding that both principles, absorption and transmission or reflection, need to be used successfully to control sound in an industrial setting. Typically, you will have a fairly broad spectrum of noise level that you're trying to deal with, and there is no single solution that is good at working at reducing that broad spectrum of noise control that you're trying to achieve. Take a quick look at some factors that affect sound absorption. If we look at the material characteristics that are relevant for a sound absorption type of solution, as I mentioned earlier, it's typically an open cell material, so looking at the fiber diameter or the dimensions of the solid portion of the material itself. So taking a look at the amount of air you have contained in the material versus the amount of material that is there could be very critical. The thickness of the material, as I mentioned earlier, as well as the density of the material. And something that also needs to be considered that often gets overlooked is the application or mounting method of the material. It's important to know that how the material is applied can affect its amount of noise reduction performance that can be achieved. Moving over to the other side of the chart, this is typically more representative of what would be called a closed cell insulation material. or a material that has more of a cell structure to it. Now, those cells can be open or closed cells, but looking at the porosity of that material, porosity would relate more to, how much of that cell structure is open cells and how many of the open cells are connected to each other, thereby creating a path that the sound energy can pass through as it enters into the material. Again, material thickness can be very, very important, as well as the application and mounting methods. So similar concepts for absorption transmission, but slightly different in terms of the types of materials that you would typically be working with. Another term that you probably will encounter fairly often is NRC, or noise reduction coefficient. It's important to understand that the NRC is not a directly measured characteristic of material. It is a calculated characteristic. It is the average of the sound absorption performance of the material at a predefined set of frequencies. And it's a specially weighted mathematical average that then gives you that noise reduction coefficient, or NRC value. When this measurement technique was originally developed, it was established with a scale of noise reduction from 0 to 1, with 0 being little to no absorption and 1 being maximum absorption. But as you can see, looking at the table, there are some numbers that show up in here in the individual absorption coefficients. And you'll see in a future slide in the NRC where you can actually get a noise reduction coefficient value greater than 1. And that is actually just due to limitations or shortcomings in the way the test procedure was defined and how the unit of absorption within the standard, or the definition of how you measure and calculate noise reduction coefficient, was originally established. So it looks weird, but you can get numbers greater than 1 just due to how the measurements are made and how the math is performed. If you look at the table in the center of this chart, you can see that materials, different materials have significantly different performance levels, both in their individual sound absorption coefficient as well as their NRC value, with the NRC value being the number at the far right of the chart. Going from materials that have very, very little acoustic performance, like marble or concrete block, to an open cell material like mineral wool insulation, where you can see the differences in the amount of performance you might get for different thicknesses or different densities of the product. A critical element to keep in mind when you're looking at this is, just because a material has a very good NRC coefficient, it may not necessarily be the best solution for the noise that you are trying to address. If you have a very specific noise level at a particular frequency that you're trying to solve, and that material doesn't have very good performance at that individual frequency. A good example of this is taking a look at the 1.5-inch 4 pound per cubic foot mineral wool, the third one down from the top of the chart. It has an NRC of 0.9, which is pretty darn good, but if your noise problem is at 250 hertz, it only has a sound absorption coefficient of 0.48, which isn't the best performance. So you might need to step up to something like the 8 pound material, which has much better performance at that specific frequency. So a very important concept to keep in mind. Two other elements to look at when you're trying to design your acoustic system is looking at the thickness versus the density of the material. Both can and will affect the performance of the material in reducing the noise level. If you look at the chart on the left, this shows some absorption coefficient data for material at different thicknesses with a common density. So the 4 curves at the top of that graph, you're looking at same density of mineral wool material, but at thicknesses varying from 1.5 inch, with the blue line being the lower of the 4, up to the same density material at 6 inches thick, the purple line at pretty much the top of the chart. And you can see the varying from a noise reduction coefficient of 0.9 to 1.1. So not a huge swing in the NRC value, but as you can see from the curves on the chart, quite significant differences in performance at individual frequency points. And then the two curves down at the bottom showing you the difference between a very open cell material like mineral wool and two other materials that, while they're not classified as closed cell, don't provide the free air path or that porosity in the material for the noise to get dampened in the material as it enters and passes through it. And so there you're looking at silica aerogel blanket, 10 millimeter thick, or the insul-thin microporous thin blanket, both of which have fairly similar absorption coefficients, but much lower than that of the open cell mineral wool. And then the chart on the right is taking a look at the impact of density. So there we have 3 examples of mineral wool that were all measured at the same thickness, but varying in density from the 4-pound 1240 material up to the 8-pound 1280 material. Here showing that density has a lower impact on the performance at the same thickness than the thickness would for the same density. And then again, comparing the density levels of the mineral wool versus that of the thin blanket solutions. And with that, we will hand it back over to Jake, and he will give you a overview of some different lab testing techniques that lead you to how in the world do we get to the numbers that I was just talking about.
Yep, exactly. Thanks, Scott. So we're just going to build on the background that we've established here and move on to some of the real-world applications of what we're looking at here. So the first test that we'll analyze is the ASTM C423 test. This one is associated with the NRC values that Scott just gave a great background on. And you can see this test involves the emittance of a sound out of a certain source in an enclosed room. What the sound will actually do is reverberate off of different panes and panels that are set up in this room, and the absorbing material that we're looking at will be laid on that yellow square in the center of the room. And what you're basically looking for in this test and what it's established for the industry is a standard practice to get you a standard number that can be compared in a normalized sense. It's been a really good test to analyze just how materials perform, how specific materials are different between any type of properties that may come up. But what the shortcomings of this test are those real-world applications. And with the ASTM test, you can kind of see what we actually have here at our technical facility at Johns Manville. We have those diffuser vanes and the rotating mic that's actually set up on a boom. When the sound's emitted, this mic will swing around and pick up the sound waves that are being emitted throughout the room, so you do get the full analysis of what truly is your sound transmission from the test. But again, this is a very standardized, simple test, and gives you some good baseline information. But we like to go a little bit deeper. So as we look to try to understand more of what a real-world application looks like, we'll go into the ISO 15665 standard, which is going to be the primary focus for the rest of this presentation. So with the ISO standard, what this is measuring, before we were just looking at an NRC value, a behavior of a material. Now we're looking at the behavior of a system. We're looking at the pipe, the insulation, and the cladding that will go around the entire system. And as the ISO 15665 standard outlines, it's measuring your insertion loss, the topic that Scott had briefed us on earlier. It's measuring how that sound is going to change once the pipe is bare, and then once you add insulation, how much of a decibel loss will you get by adding that acoustic system. ISO establishes three main classes for performance. You have Class A, Class B, and Class C. These kind of go from Class A being the easiest to meet, with Class C being a little more difficult. But as the industry has gotten more accustomed to the system, there's actually been a fourth class that's been thrown out there by one of the major petrochemical players in the market. And this Class D is the hardest to reach out of any of the classes established in the ISO standard. And another thing about the ISO standard that I'll brief before we move on, ISO is very particular in what they give their classifications to. So that means that as you go about testing for a system, you have to test as close and almost exactly to the insulation system as you can to get those ISO certifications. So that means using the exact insulation that you tested in your lab test, the same system, and keeping everything, even the manufacturer, consistent. So even deeper in the ISO classes, it establishes three different pipe size ranges, the smallest being anything less than 12 inches in diameter. What's most popular and most common out there in the market is that mid-range pipe size 2, which is anywhere from 12 to 26 inches in diameter. That's more because that's the easiest, most available testing size that's arranged. But what's less frequent out there is the pipe size 3, and that's getting into the large pipe sizes that you see more in the industrial markets and industrial plants that we encounter and need to develop systems for. Again, these pipe sizes, especially when it comes to the ISO standard, they kind of start easier to meet around pipe size 1, and they get gradually more difficult to meet as you get higher in pipe sizes. So this slide is showing the requirements for the ISO standard, specifically referencing insertion loss requirements. I'm not going to dive too much into this, but just want to reiterate the fact that as it goes from A to D and sizes 1 to 3, you see those requirements get a lot more difficult to meet. And the important thing here is, in order to get an ISO certification, you have to meet every single octave band frequency in the ISO standard. So you can't have 4 out of 7, 5 out of 7. You have to meet every single requirement across the entire breadth of the standard to get that classification. And something to point out that we mentioned before, we've got a couple of negative numbers. Those are real numbers on your screen. Those are more of an understanding that ISO in the industry has come to when it comes to those low wave frequencies. The low frequencies have a tendency to behave oddly just because of the nature of the wave itself and the inconsistency. So you sometimes have, even if you're putting proper sound absorbing or any other acoustic insulation on a system, you will have some interesting numbers, and ISO has identified that and incorporated that into their standard. So just to kind of recap, we've got, starting from the top left to right, you've got the bare pipe, and moving on to the other pictures, you see our initial layer of mineral wool that's applied to the bare pipe after the initial pipe sound acoustics have been measured. And then we start going with the rest of the system, including the mass-loaded vinyl layer, and finishing with the bottom right with the cladding. And similar to the ASTM method, there's a rotating boom mic that is stationed specifically in the room that's picking up the sound throughout the test, and then those final numbers are measured and incorporated into the final report. And again, meeting all of the requirements that are set up in the ISO standard are necessary to have your final system ISO certified. And to get into some of the results, I'll let Scott take over and talk about what we were able to accomplish here at JM.
Excellent. Thanks, Jake. Great overview of the ISO standard and setting the groundwork for taking a look at the systems that JM has been able to develop that are certified to that standard. We'll start off with the easier classifications to meet, as Jake mentioned, the Class A and B systems. I will note up front that for all of our systems, the Class A, Class B, Class C, and Class D, we tested to the most difficult or most stringent requirement within each class, which would be the pipe size 3 requirement. So that you'll see as we talk about each of our systems how they are certified to meet the requirements of A3, B3, C3, or D3, because that is the pipe size configuration we tested for trying to meet the most difficult requirement. Our Class A3, B3 system is, as you can see in the picture on the bottom right, it is 2 layers of 2-inch thick Manville 1200 pipe insulation, a single 1 pound per square foot layer of mass-loaded vinyl, and then a aluminum cladding on the outside of the mass-loaded vinyl of a 0.016-inch thickness or greater, but we did achieve it at an 0.16-inch thickness, excuse me. So this does meet the requirements of the A3, B3 system, as I said, and so can be applied for either of those. Then moving on to the next more difficult configuration, that being the C3 configuration. You can see that it is very similar to that of the A3, B3, only it adds a second layer of mass-loaded vinyl. So it again starts with 2 layers of 2-inch mineral wool 1200, but then has 2 layers of 1 pound per square foot vinyl. Now you could utilize a single layer of 2 pound vinyl instead of 2 layers of 1 pound. But we did it with the 1 pound for this testing because, again, we were working with the larger pipe diameters, and that lighter material was easier to work with in the installation process and setting up for the testing. And then in this case, the outer jacket does change from the 016 aluminum used for the A and B system to an 020-inch stainless steel. And this system, as you can see, does meet the requirements for the C3 as well as the subclasses of A3 and B3. And then moving on to the most difficult requirement, that being the Class D, and again, the pipe size 3 grouping. This system changes in a couple different ways from the B3, C3 systems. As you can see in the picture, we do have an initial layer of mass-loaded vinyl in between the 2 layers of mineral wool. It is the same 2 layers of 2-inch, but there is that single layer of 1 pound vinyl in between the 2. Then we have 3 layers of 1 pound vinyl over top of that, and again, that wouldn't have to be 3 layers of 1 pound. It could be a single layer of 2 pound and single layer of 1 pound, or if you really wanted to be bold, you could go with a 3 pound if you could lift it. And then again, using the same 020 stainless steel as the C3 system used. And then again, you can see from the information in the chart that this does meet all of the requirements of the D3 as well as the A3, B3, and C3. So you can see that as you step up in the difficulty of the noise reduction requirement from the Class A to Class D, the configuration does get more complex, so it is more difficult to achieve that level of sound reduction. We do, and here you can see just a quick summary. We won't spend a lot of time on this, but just quickly summarizing the different systems we have. So the AB system, the ABC system, and then the ABCD system with those same representations as far as the configuration is concerned. We do have one additional configuration that has been certified for some of the simpler noise reduction requirements, smaller diameter and lower levels of noise reduction or insertion loss requirement. We do have a certified configuration for the A2 classification. So this would be the mid-grade pipe size requirement, as Jake mentioned when he was talking about the ISO standard. And we actually have two configurations that meet this. It can be met with a single layer of 1.5 inch thick Manville 1200 pipe insulation, or it could be met with 2 layers of 2 inch for a total of 4 inch of the same Manville 1200 of pipe insulation. The value of showing 2 different configurations here can relate to what I will discuss in a minute relative to combined thermal and acoustic systems. So this would show that if you had a thicker thicker thermal requirement, you could still achieve the acoustic requirement that you had with that thicker system. And then just summarizing again quickly, we did do all of our testing to the most stringent pipe size, that being the 3 classification. Most of the ISO certified systems that you see out in the market have been tested to the 2 size. So you'll see configurations certified to meet A2, B2, C2, D2. It's important to know that you cannot assume that an A2 system meets the requirements of A3, because the acoustic behavior of the larger pipe size is different and does need a treatment specific to that diameter and mass of pipe. Likewise, you can't assume that a B2 meets the requirements of B3, and same for C and D. So it's very important that if you do have larger pipes on your facility, that you are utilizing systems that have been certified to the pipe size 3 classification requirements. All of our configurations only use 3 different layered components, so the mineral wool insulation, the mass-loaded vinyl, and the metal. And we supply all 3 of those materials, so you're able to source the entire system from a single supplier. And then again, the class D3, which is the most difficult of everything to meet, is one of the ones that we do have a certified configuration for. And then a couple things to keep in mind is that you can utilize the information that we've reviewed here today and apply engineering judgment to look at the insertion loss results that are achieved in each of the 4 classifications that we have, and determine how they can be applied for other requirements you may have. We have, as I said, tried to certify everything to the most complicated requirements, so that then the designers can take a look at what might be the optimal solution for the particular project that you're designing that acoustic system for. Our acoustic systems have a maximum metal jacket thickness of 0.20 inches, as we described earlier. There are several systems out there that actually require a much thicker metal requirement, 0.40, and that's basically to achieve a higher level of mass on the outer layer. And it's important to know that that typically would be a requirement for 2 layers of 0.20, and that is going to add more cost in terms of labor for installation, as well as other issues. And as Jake pointed out earlier, it's very important to remember that materials are not interchangeable. So you can't substitute a different mineral wool material for the material that we have certified in here, and assume that it's going to meet the requirements. That configuration, that specific material does have to be independently tested and certified to make sure that it meets the ISO requirements. Real quick touch on some design considerations, as I mentioned, for thermal and acoustic systems, and just hit on 2 highlights here. If you are using a rigid insulation for your inner thermal layers, like a calcium silicate or a perlite or cellular glass on a cold system, or PIR, polyiso, It's important to know that you must take the combination of the pipe diameter and the thickness of the insulation that is going around the pipe into account when you look at what the what ISO class or pipe size requirement you have to meet. So if you have a 10-inch pipe with 2 inches of insulation, you actually need to treat that as a 14-inch pipe, not a 10-inch pipe. The other critical aspect to keep into account when you're looking at a thermal and acoustic system is that you, depending on the material being used for your thermal insulation, you can take advantage of the acoustic contribution of the thermal material and vice versa, the thermal contribution of the acoustic material, and come up with a system that is thinner than the sum of the 2 individual systems. So if you need 2 inches of thermal treatment and 2 inches of, or 4 inches of acoustic treatment, you don't necessarily need 6 inches of insulation. You may be able to use one to count toward the other and come up with a thinner overall system. And with that, I will pass it back over to Kim Melton, who will wrap up with a few other pieces of information for you.
Thank you so much, Scott and Jacob. This was a great presentation today. I'm going to go ahead and talk through a couple of additional resources that we have for anybody who's looking for more educational resources like this webinar that you've attended today. The first one I want to talk about is Insulation Intel on the Source. And the Source is our online repository for all of our educational content. So that includes our recorded webinars, ebooks, links to our latest blogs, technical documentation that might be helpful, descriptions of each of our products, and then online tools. So this is going to be things like the Smart Binder app, where we house, you can download all of our data sheets to your cell phone, or the NEMA 3E Plus app, or not app, I guess, tool that you can use on your computer to determine the appropriate insulation thickness you need of JM insulation for your specific application needs, whether they're energy efficiency, environmental aspects, or yeah, I think those two. So you can access the Source directly from our industrial homepage. So there are 2 ways to get there. The first is on the homepage for industrial. On the left side, you'll see a menu that says Webinars on Demand. That'll take you to the tab directly with all of our webinars. And this webinar will be recorded and posted up there. And then you can also access it from the menu on the right side where it actually says the Source. Also, we have technical support. So if you have any questions technically related and you're looking for somebody to talk to, and even there are some questions that were submitted here today that we'll probably follow up with you privately because they're not quite appropriate for the webinar. If you have questions, though, this is the phone number you want to call. You'll be able to access somebody to talk to about whether it's updating your specifications, whether you need product information, whether you want to talk to a salesperson. This will be able to direct you to the right person to help get your questions answered. So this is a phone number you will want to take down if you have any questions after the webinar. Finally, I did just want to highlight our Engineer Advisory Council. So once the COVID-19 chaos sort of dies down, we are going to go back into housing what are called Engineer Advisory Councils. And these are opportunities for engineers in the industry to meet with us to talk about their pain points and what we as a manufacturer can do to better support you. So this isn't necessarily a sales thing. This is your opportunity to make sure that you're getting what you need directly from manufacturers. This is a half-day enterprise, and you will receive a certificate of completion for 4 hours of continuing education credits. So if you're interested in participating in this, you can let us know in the survey, and when we are free to have another one of these, we will reach out to you and go ahead and get the ball rolling on that front. Finally, certificates of completion. So everybody will have a certificate of completion. These will be sent to you by next Tuesday, and they'll arrive in your inbox. This can be submitted for professional development hours. One thing to note is it is up to your basically governing body for your professional development hours whether or not they choose to accept the certificate. And then, as I said earlier, we will post a recording of today's webinar online. It will include the questions so that you'll have the webinar in its full context, but we don't actually send a copy of the webinar, like the slides, out to people. But we will send an email to you when that is live online. So with that, Scott and Jake, are you ready for some questions?
Absolutely.
Excellent. So I'll start with Jake on this one, and that is, what instruments are used to measure acoustic sound?
Yeah, so the instruments that are typically measured to measure sound, especially in the tests that we've described previously, would be those boom mics. And what those mics are able to do is, because they're rotating, they're not just picking up sound in one specific area of the room, because we know in any acoustic settings, and some famous ceilings have made this even more interesting, but the room has a big factor on how much of the sound is actually being picked up. So the rotating boom mic is the primary instrument to record the sound at these various frequencies and is used as the standard in a lot of the labs around the world.
All right, thank you. The next question is, to achieve a proper noise insulation, not only the insulation and material jacketing, but also the support of those is important, especially on vertical lines or equipment. Can you please provide some examples of a state-of-the-art technique?
Okay, this is Scott. I'll try to take that one. That's actually a fairly complicated and involved discussion. You are very, very correct in your statement that there are other factors that will affect it, not just the acoustic treatment you apply. We touched on a couple of those issues in the discussion related to having to isolate things mechanically, and I think that might be what you're referring to. On vertical pipes, you do have to have additional support mechanisms to hold the pipe and the insulation in place. And if you would like to get into a more involved discussion on that, please reach out to us. Let us know through the survey questionnaire at the end, and we will have one of our technical folks reach out to you and discuss that with you in much more detail.
Thank you, Scott. And also, as you can, if you're still looking at your screen, I've put the technical support phone number up there in case anybody would like to contact us directly. The next question, and I'm going to couple the next two questions, is the first one is mineral wool 1200 insulation non-combustible? And does JM have plans to test the Manville 1200 insulation in accordance with the IMO fire test procedures code for installation on ships and offshore units?
Hey, Kim, I'll field that one. That's a great question, and it's one that comes up a lot with mineral wool products. Especially in the mineral wool / rock wool industry. Non-combustibility is a big factor in one of the benefits of mineral wool. And so JM's products, specifically what we talked about today, was our Manville 1200 water repellent pipe. And this product has been tested for non-combustibility according to both the ASTM E136 standard and the ISO 1182 standard. And both of those have received passing results fairly easily in accordance with the properties of mineral wool, just because it's so robust and the material is so good in fire protection applications. One of those important things can be linked into the IMO, the Marine Organization standard. What they normally look for is that non-combustibility trait within their materials, and so mineral wool fits right in there. The thing with that type of specification, though, for IMO is they require specific materials to be specified there. So JM has specialty products that adhere to those specific IMO standards, and those are our Manville marine pipe insulation, our Manville marine industrial board, and our Manville marine A60 and A30 board for those decks and bulkhead applications. That's a really good question, and it gets deep into the true behaviors of mineral wool.
Great, thank you, Jacob. So as we are approaching the top of the hour here, I do want to let you guys know that we will answer questions up to 15 minutes after the hour. And any questions we don't get to today or that are submitted in the survey after the webinar, we will answer you directly in follow-up after the webinar today. So the next question to the group is, the intuitive wisdom is that the more compliant the insulation, the better the noise reduction. The higher the mass of the jacketing, the better the noise reduction. That even minor voids or openings in either undermine effectiveness, and that coupling via solid pipe supports must be avoided. Can you go into some detail that explains whether these rules of thumb are valid or not, and what are any limitations that they might be?
Yeah, thanks, Kim. That's also a very, very good question, and it does highlight some critical aspects of designing and installing acoustic insulation treatment systems. As is true with thermal insulation systems, in an acoustic system, the quality of the installation is very important. So you can have the very best material from an absorption or sound transmission standpoint, but if the material is improperly installed, it definitely will not perform as designed or as specified. A couple of the key factors are those elements that the question stated. If there are gaps in the material, the noise is going to find those points that it can get out more easily, and it will come out through those gaps, either in the insulation material itself, the absorbing material, or in the case of mass-loaded vinyl, if there's gaps there, it will come out there as well. So yes, it's very important for the material to be properly installed, as well as selecting the most appropriate material for what you're trying to achieve in your design.
Excellent. Thank you, Scott. So the next question for the two of you is this. Regarding the installation of a control valve and calculating the noise coming from the valve, what is the standard sound credit in negative dBA that could be deducted from the noise created by the valve? So if the valve creates a 90 dBA of noise, what's the standard deduction when insulation is added?
You want to get that one, Jake, or you want me to tackle it?
I can speak to it a little bit. It kind of builds on what Scott's already referenced. With any insulation system, and especially getting into specific insertion loss or decibel reduction type investigations or requirements, things get very interesting just because everything is impacted by the type of insulation that you apply, the amount that you apply, and as Scott mentioned, the way that you apply it. Those are three main things that affect how much successful sound reduction you're truly going to get out of any system. So as far as a standard number, there's not one that's truly out there, like a decibel reduction per inch. As much as we'd like that, that's not really an effective way to measure everything, which is why these standards are so particular by themselves, is that there's so many variables that are so difficult to control, and we've tried to do our best to make that system as robust as possible. So in regards to that question specifically, there's no one answer, but as we always recommend, it's important to truly know the behavior of the material that you're putting on any areas that you're looking to reduce sound, and doing those effectively through the procedures that Scott laid out to truly reduce the effects of sound in your system.
Great, thanks, Jake. The next question, I don't know that we'll know the answer to this, but I'm going to pose it to you guys anyway. So if 85 to 90 dBA is for 8 hours, what is the max SPL for exhaust valves or vents that would only operate for 1 to 2 minutes once a week?
I don't know about you, Jake, but I am not aware of any standards or regulatory limits that are out there in that type of restriction or that type of definition. Most of the standards do relate to noise exposure over a fairly long period of time, because they're typically representative of a work day, and it is typically ongoing exposure that is more damaging to your hearing than just short duration exposure. Are you aware of anything, Jake?
As far as any standards go, I'm not aware of any specific numbers that are there. OSHA may have some more information on burst exposure for those one-off applications. Those are a lot more tricky to handle and require different approaches to how to truly affect the sound sound effects that somebody in that area might really get from being around that source. So as far as a standard number, there's not one that comes to mind, but looking more into those short terms, you know, when do eardrums start being affected? When does the human body get affected by whether they're vibrations or the effects of that decibel limit? That's more of a better investigation towards that one-off type scenario. But especially with what we focused on today, a lot of that goes into, as Scott was mentioning, the pipe systems, continuous systems that will emit these sounds, you know, 24/7.
Great, thank you guys. Jake, this next question is for you, and that is, what is the difference between actual insulation density and nominal density, and where did nominal density come from?
That is a great question that has been hanging around the industry for a while. The difference truly is nominal has been established as a quote-unquote maximum value that came with the ASTM standards a while ago. It was basically developed to make sure that insulation manufacturers weren't skirting any limits or making products that didn't adhere to either their standard or their own company standards of quality. So nominal density is typically, and when you see it in specifications, nominal basically adds a 20 to 25% fudge factor, which is definitely a colloquialism to use my own approach to it, but it's more of analyzing the standard and what the standard sets versus what is actually happening with the manufacturing process. So actual density has been something that, especially at JM, we've done as needed, but the actual density is the real density that you see, and the nominal density is basically 25% more than the density you're actually getting.
Great, thank you so much, Jacob. Scott, the next question is for you, and that is, what is the difference between mineral wool and rock wool?
They are basically two names for the same material.
Excellent. I'm going to pose this to both of you. I'm not sure who is best to answer it. So that is, do the Class A, B, and C pipe systems actually increase the noise level at low octave bands?
Excellent question, and I think Jake touched on that during his discussion on what the ISO standard is when he was talking about some of those negative numbers on the Class A, B systems at the lower frequencies, and basically what you are seeing and why you see those negative numbers is the addition of the acoustic insulation system, so the insulation, any mass-loaded vinyl, and any jacket to the pipe to reduce the noise level at the mid and upper frequencies can actually make the noise level at the lower frequencies worse. So if you may have started with a noise level at 250 hertz of 80 dB before you had any treatment on there, after the treatment was added, you might actually be at 85 dB. And so the ISO standard accounts for the fact that the addition of the mass to the system as well as the change in the outer diameter and circumference of the system can actually make the noise levels at lower frequencies worse.
Great, thank you, Scott. The next question is for you, Jacob, and that is, for the JM pipe lagging configurations, what is the max allowable temperature of the pipe? Could we use it for lagging muffler piping, 12 inches to 26 inches, with temperatures ranging from 850 degrees to 1200 degrees? I'm not sure what the max temperature on the mass-loaded vinyl is.
Yeah, that's always a great question. Looking into what the exposure is to any system, we've got our mineral wool that's been rated to up to 1,200 degrees Fahrenheit for applications just like you've described. And the way we've set up the system is, so mineral wool is doing most of the application and doing most of that heat absorption, especially at 4 inches. Mineral wool is doing most of the heavy lifting when it comes to doing the true insulation of any system. So if 4 inches of mineral wool is all you have, the better question would be once all the factors from your system are put into any calculation or any modeling system like 3E Plus or anything else that's out there, looking into what kind of heat is that mass-loaded vinyl truly seeing, and then we can do that final evaluation of, is that going to be a good system for you? Because without the inherent data and doing the calculations, that's something that we can't really figure out. But that's why Kim has shown this technical support, and we've given these resources both available on the source, the 3E Plus tool, as well as a couple other informations about our products. Just because there's so much that goes into these systems that we're here to help every step of the way.
Great, thank you, Jake. Scott, you touched on this a little bit in the presentation, but if you could elaborate on it, what makes mineral wool so good at sound absorption?
It is the structure of the material, so it's that primarily the fact that it is an open cell material, so there is what's known as a free air path for the sound waves that are airborne to actually enter into and try to pass through the material. And so as those sound pressure waves try to pass through the material, they will lose velocity and lose strength, so to speak, and they will actually get absorbed in the material. So it's that going back to that combination of what's the fiber size, the fiber diameter, the density of the material, all of those factors come into play and determine what the complexity of that free air path is, and the more complex the path is, the better sound absorption you're going to get.
Great, thank you, Scott. The next question is a two-part question, and the first part is, wouldn't the wool be much better for sound absorption or reduction instead of cladding? And is the purpose of the cladding mainly to protect from the weather? Scott, can you take that one?
Sure, you're absolutely right. Good question. The primary function of the cladding is to protect the mineral wool not only from the weather, but just from damage, from people, from things falling on it, from whatever. But as Jake was mentioning when he was talking about the ISO standard, the ISO standard requires that you test the entire system, not just necessarily the materials that may be specific to the sound reduction that you're trying to achieve. So yes, it is typically the mineral wool and or the mass-loaded vinyl that's doing most of the heavy lifting, so to speak, in terms of reducing the noise levels. The jacket will add some level of mass to it, so it will contribute, but the ISO standard requires that you test the full system. So you can't just test the mineral wool and then assume that you're going to get the same performance when you put something else around it.
Great, thank you, Scott. Jake, the next question is for you. And was it the water repellent JM Mineral Wool 1200 that was used in the ISO 15665 testing? And if not, do you expect any difference in the results because of the water repellency?
Thanks, Kim. That's definitely an important question. So the water repellent pipe was used for this application. So the Minwool 1200 that the Mineral 1200 pipe that we mentioned before, and Scott listed in those designs earlier, those would be the ones that would pass the ISO classification. So handling that is a big part of your entire insulation system, looking at, you know, thermal, acoustics, and then any corrosion or exposure, and having that as a part of your whole system is kind of what makes this all great. I think that covers it. Is there anything else that we need to hit there, Kim?
No, that's it. And you know what? I think I'm going to go ahead and call it right there. We're just coming up to 15 after the hour. So everyone, thank you for your time. If we didn't get to your question today, we will reach out to you privately to make sure your questions do get answered. If there's anything that you think of after the presentation that you'd like to know, again, you can reach out to us via this phone number here on your screen right now, or you can ask it in the survey, and we'll follow up with you in the survey as well. So again, thank you for your time. Jake, Scott, thank you as well. It was a great presentation today, and we hope you guys have a great rest of your week.
All right. Thanks for joining us, everybody.
Yeah, thank you, guys.